Factoring polynomials is a really important concept in algebra. We use it when we're simplifying rational expressions and other complicated mathematical structures. In this video, we're going to talk about factoring quadratics when the a value or the lead coefficient is 1, as in this example right here. What I want to say though, it's really important that the way that we factor these is really different than the way that we factor quadratics that look like these. These are both quadratic trinomials. The difference is the lead coefficient in this case is a 1. The lead coefficient in this case is not 1. We'll talk about factoring these in a different video. What I'll be using for this generally is either the AC method, which is my favorite way of factoring these quadratics, or the guess and check is a very, very popular method. I'm going to start by showing you how we factor this. I'll prove that we have the factored version. At the end of the video, I'll describe why we're able to factor in this way. To factor a quadratic where the a value is 1, we analyze these coefficients, the constant coefficient and the linear coefficient. What we're looking for are two numbers that multiply to be this negative 36, but add to be the negative 9. Before we answer that question, we know that a quadratic with a lead coefficient 1, if it factors, will factor into two binomials that each have an x as a first term. The second terms are the answer to the question we just talked about. These will be the numbers that multiply to be negative 36 and add to negative 9. When we're looking for two numbers that multiply to be negative 36 and add to negative 9, there's a lot of different tricks that we can use to make this easier on ourselves. First and foremost, if we have two numbers that multiply to be a negative 36, we know that one of those numbers must be a negative and the other one must be a positive. That's the only way to get two integers that multiply to be a negative number, if one is negative and one is positive. We also know that if they add to be a negative number, that the negative of these two must have the greater absolute value. The way that I then attack this is I focus on the multiplication first. I'm going to write a factor tree for 36, which represents all of the whole number factor pairs that multiply to be 36. You won't always need to make a factor tree like this, but if you're ever stuck in answering a factor question like this is a really good way forward. Here I have all the whole number factor pairs of numbers that multiply to be 36. What I'm now going to do is give the negative to the larger side of these numbers. And what this means now is this is 1 times negative 36. In this case, each of these factors now, factor pairs, will now multiply to be negative 36. The only question I need to answer now is which one of these pairs also add to be a negative 9. After looking at this, I see that 3 plus negative 12 here equals a negative 9 if I add these two numbers together. These are my two numbers that answer the question. Going back to here then, what I get is a plus 3 and a negative 12. So the statement that I'm making is that this right here, x plus 3 times x minus 12, when multiplied would result in the original quadratic of x squared minus 9x minus 36. I'm now going to multiply out these two binomials together to one, show you that yes, they do multiply to become x squared minus 9x minus 36, but also when I do that, you'll see why this trick works. So when I multiply, I FOIL these together, I get x times x to give me an x squared. That's my x squared there. I get an x times a negative 12, which is a negative 12x. Then I also get a 3 times the x to get a plus 3x, and then the 3 times the negative 12 to get the negative 36. So when we combine these together, we'll combine the like terms of negative 12 and a plus 3x. This gives us our negative 9x and the negative 36. This is why this method of factoring actually works. Where did the negative 36 came from? It came from multiplying the 3 times the negative 12. Those two numbers together multiply to be negative 36. They give us that constant coefficient. The reason then we also want those to add to be this middle coefficient or the linear coefficient is because of this move right here. When I combine these like terms, because of these x's in both of these terms, when I add these coefficients together, it's adding the negative 12 and the 3, which gives me the negative 9x. And when I simplify this, I do get my original quadratic of x squared minus 9x minus 36, meaning x plus 3 times x minus 12 is the factored version of x squared minus 9x minus 36.